Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is hydrogen. Hydrogen is the most abundant element in the universe and the third most abundant element found on the surface of Earth's crust. It is visualized as the major future source of energy and has the simplest atomic structure amongst all the elements. It just has one proton in its nucleus and one electron moving around it. In elemental form, it is formed as a diatomic molecule, H2 or dihydrogen, and it is the first element in the periodic table and is placed on top of the group 1. One electron in its outermost shell and can be placed over group 1, but it can also be placed above halogens because it has one electron less than the noble gas configuration. So it has resemblance with both alkali metals and halogens, but at the same time it has some differences with these elements also. Its ion is very small, extremely size, 1.5 into 10 raised to the power minus 3 picometer. So being so small, it does not exist freely, but it is found associated with other. For example, ammonia can take up one hydrogen ion to form ammonium ion. It is best placed separately in the periodic table because it's unique in behavior. To its light nature, it is much less abundant, about 0.15% by mass in the Earth's atmosphere. In the combined form, it forms 50.4% of the Earth's crust and oceans. It is formed in plant and animal tissues and is a constituent of carbohydrates, proteins, hydrocarbons, etc. Different isotopes are protium, deuterium, and tritium. They differ in the number of neutrons. Protium has no neutron, deuterium has one, and tritium has 2 neutrons. Preparation of dihydrogen. Laboratory method. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. So the reaction is the hydrogen ions of hydrochloric acid will be taking electrons given by zinc to form zinc ions and dihydrogen. It can also be prepared by reaction of zinc with aqueous alkali. For example, zinc plus NaOH gives sodium zincate and hydrogen. Electrolysis of acidified water using platinum electrodes. Dihydrogen will be obtained. Then high purity dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. It is also obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by electrolysis of brine solution. During electrolysis at anode, chloride ions give electrons to form chlorine. At cathode, water takes up electrons to form dihydrogen with hydroxide ions, and overall reaction is 2 sodium ions plus chloride ions plus water gives chlorine plus dihydrogen plus sodium ion plus hydroxide ions. Action of steam on hydrocarbons or coke at high temperature in presence of catalyst. For example, hydrocarbon with steam at this temperature using nickel as catalyst, a mixture of carbon monoxide and hydrogen is formed. This mixture is called water gas. Similarly, methane will react with steam to form water gas. It is also called synthesis gas because it's used for the synthesis of methanol and a number of hydrocarbons. Nowadays, synthesis gas or syngas can be obtained from sewage, sawdust, scrap wood, newspaper, etc. Then we can obtain this syngas from coal also by passing steam over it at this temperature. 1270 Kelvin. The reaction is called coal gasification reaction. The products of hydrogen can be increased by reacting the carbon monoxide of the syngas with steam at this temperature and using iron chromate as catalyst. Carbon monoxide gets converted to carbon dioxide and dihydrogen is obtained. This reaction is called water gas shift reaction, and the carbon dioxide formed is removed by scrubbing with sodium arsenide solution. Presently, about 77% of industrial hydrogen is obtained from petrochemicals, 18% from coal, 4% from electrolysis, 1% from other sources. Water is an important constituent of living organisms. In the human body, about 65% is water. In some plants, you can find even 95% of water. It is the crucial compound and is necessary for survival of all life forms. It is also a solvent of great importance. The distribution of water in the Earth's crust, we find of the total water content, 97.33% is in oceans, 0.008% in saline lakes and inland seas, 2.04% in polar ice and glaciers, 0.61% as groundwater, 0.005% as soil moisture, and 0.001% as atmospheric water vapor. 0.0001% is in rivers. Physical properties of water: it's a colorless, tasteless liquid and has unusual properties in condensed form, that is in liquid and solid state. This is because of hydrogen bonding in liquid and solid state. The different physical properties of water are: molecular mass of water 18.051 gram per mole, whereas heavy water, deuterium oxide, has molecular mass 20.0276. The melting point of water is 273, of heavy water is higher. Boiling point to 373, 374.4. Then enthalpy of formation in kilojoules per mole is 285.9 kilojoules per mole, whereas for heavy water it's higher. Enthalpy of vaporization at 373 Kelvin in kilojoules per mole is 40.66 for water, 41.61 for heavy water. Enthalpy of vaporization is 6.01 for water. Temperature at which water has maximum density is 276.98. Heavy water has maximum density at 284.2 Kelvin. Density is 1 gram per centimeter cube. Density is greater than 1 grams of heavy water. Viscosity is 0.8903 centipoise. Viscosity is 1.107 centipoise. Dielectric constant for water is 78.39. For heavy water it's 78.06. And electrical conductivity is very low, 5.7 into 10 raised to power minus 8. So as compared to other components, water has high melting point and boiling point, high enthalpy of formation and vaporization as compared to H2S and H2SC, other members of oxygen family. Then it also has higher density, specific heat, thermal conductivity, surface tension, dipole moment and dielectric constant than other elements. The high heat of vaporization and heat capacity results in moderation of climate and brings the body temperature of living beings and regulates the body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plants and animal metabolism. And due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates dissolve in water, so it's a good solvent. Structure of water: in the gas phase, it has a bent structure with 104.5 bond angle and 95.7 picometer. It's polar in nature, with oxygen-hydrogen bond being polar. The hybridization is sp3, and of the 4 sp3 hybrid orbitals, 2 contain shared pairs of electrons between oxygen and hydrogen, and 2 contain lone pair of electrons. Bond angle is reduced to 104.5 degrees. In the liquid phase, water molecules are associated together by hydrogen bonds. In the crystalline form of water is ice. At atmospheric pressure, ice will crystallize in the hexagonal form, but at very low temperatures, it will crystallize in the cubic form. The density of ice is less than water, therefore ice floats on water. This fact is helpful in ecological balance. In winters, ice forms a upper covering of water bodies, providing thermal insulation and survival of aquatic life forms like animals and plants is possible because of thermal insulation and ice being bad conductor of electricity. The warmth of the water body remains intact. Outside cold temperatures do not cool the water because of thermal insulation provided. Structure of ice. Ice has highly ordered 3-dimensional hydrogen bonded structure in which each oxygen atom is surrounded tetrahedrally by 4 oxygens at a distance of 276 picometer, and each oxygen is bonded by covalent bonds to 2 hydrogens and by hydrogen bonds to other 2 hydrogens. So each oxygen is also surrounded tetrahedrally by 4 hydrogens. So hydrogen bonding gives ice a rather open type of structure in which there are empty spaces or holes, and these holes can hold some molecules of appropriate size interstitially. Thereby the density of ice is less than that of water. Chemical properties of water. Amphoteric nature. As an acid, water will react with basic substances like ammonia to form hydroxide ion and ammonium ions, and as a base it will react with acidic substance like hydrogen sulfide to form hydronium ion and hydrogen sulfide ion. The autoprotolysis or self-ionization reaction involves water will ionize into hydronium ions and hydroxide ion. Here this water is giving a proton, so acting as acid. This is accepting a proton, so it's acting as a base. After giving proton, it forms its conjugate base, hydroxide ions. So this is base 1 of acid, conjugate base of acid, and this is conjugate acid of base, because after accepting a proton, it has a tendency to give a proton and is acting as an acid. Redox reactions involving water. Water can be easily reduced by electropositive metals. For example, with sodium, it gets reduced to dihydrogen, so acts as a good source for hydrogen. And it can be also oxidized to oxygen. For example, during photosynthesis, water is oxidized into oxygen. Carbon dioxide gets converted to glucose. And it can also be oxidized with fluorine, and fluorine reacts with water to form HF and oxygen. Hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency and dissolves many ionic compounds. However, certain covalent and ionic compounds are hydrolyzed in water. Hydro means water, lysis means breakdown, so they are broken by water. For example, phosphorus pentoxide will be broken down into phosphoric acid by water. Similarly, silicon tetrachloride will be broken down, water will break and add up to form silicon dioxide and hydrogen chloride. And nitrides react with water, water breaks up hydrogen gets attached with nitrides to form ammonia, and hydroxide ions are also released. Next is hydrates. So water can also form hydrates. From aqueous solution, it can be certain salts can be crystallized as hydrated salts. For example, copper sulfate pentahydrate. Such an association of water is of different types. The water which is attached to hydrated salts may be coordinated water, interstitial water, and hydrogen bonded water. For example of coordinated water, chromium hexahydrate contains water coordinated to chromium atom, and 3 chloride ions will be outside the coordination complex. And in barium chloride dihydrate, water is present in between the spaces of barium chloride molecules. This is interstitial water. In case of copper sulfate pentahydrate, 4 water molecules are coordinated, form coordinate bond with copper, and tetra aqua copper sulfate, and 1 water is hydrogen bonded to water molecule. So that's all in today's topic. If you like the video, please do share and subscribe. Thank you. Have a nice day.